So we are back, and so Andy, I leave the floor to you.
Okay, I'm going to give a brief overview of how you might do an X-ray timing analysis for the XRT on Swift, using an example from a source called MaxEJ 1659-152. So this was a MaxE detected black hole X-ray binary. I think it was detected in 2010, which Swift has a program to follow these transients up, and we got a nice data set on this. So the image in the top right shows you the PC mode image for this source. It was so bright that you have a hole in the center of the PSF there, because the grade migration causes us to lose all the grade 0 to 12 events when it's so piled up. You see that hole. So this is a particularly bright source in PC mode, but I'm going to use the windowed timing data for this example. What we can use the PC data for is to attain the source position. You can install the user object page will fit a PSF profile which accounts for the hole in the middle for the pilot, and it will still give you a very accurate position. So I used user objects initially to generate that image and to get the source position, because when we do the window timing analysis, Kim mentioned earlier, it's always good to give the pipeline the exact source RA and source depth, because especially in window timing mode, because it's one-dimensional, it uses the position. It predicts where the source should be on the detector to make the timing analysis, time tagging of the events more accurate. So it uses the source RA index, inverts where that should be on the detector, and it can work out a more accurate time tag for each event. So that command line there is what I gave XRT pipeline to process this data. So Kim said you can type XRT pipeline, it will prompt you for the relevant things, but this is how you can do it all in one go on command line. So I give it the input directory, the output directory, what's called the STEM inputs there. That's just the FW for Swift and the observation ID. I'm concentrating on the pointing data set, so I don't care about trying to process the slew of settling data. So I give obs mode equals pointing, and the data mode is WT for the window timing, because there's a mixture of window timing and PC data in this observatory, as well as the source RA index. The XRT pipeline will go away and process the data, and it will actually generate a light curve. Is it 1 second binning by default for window time? Well, in 1 second binning by default. So the light curve I've plotted quickly with fplot. Fplot is one of the simple F tools to let you plot things from binary fixed tables. In this case, the light curve file has 2 columns or 3 columns: time, rate, and the rate error. I'm just going to plot here the time with the light curve bins against the measured count rate. So this is literally the observed count rate, which comes from default from I think a 20 pixel extraction region, but I will use a different region later. And this lets me just do a quick inspection of the light curve. You can see there it's built up of many snapshots, and I think it's probably over the weekend. So it's a long duration data set. But from this point on, I'm going to concentrate on the very first snapshot, because that shows a very interesting quasi-periodic oscillation. So this is all horrible command line tools that we use. It is very important to adjust because when Swift measures your photon arrival times, it's all done according to the spacecraft clock on board the spacecraft. So we need to adjust these times to the solar system barycenter, and there's an F tool called BaryCore which will do this for us. It literally corrects all the event times and any timing keywords in the event file to that of the solar system barycenter. It's very important if you're looking for periodic signals like pulsars. For example, if you don't do this on the crab data set, you won't see the pulse signal. It's very difficult to see otherwise. So this tool, BaryCore, needs the satellite attitude and orbit file, which is in your auxiliary data directory. It's called the SAO file here for short, and also the source RA index. So that is the command line you can give for BaryCore. Again, it will prompt you if you don't give all the the
Excuse
input,
me.
and that will then correct the times.
Excuse me. Can you please show the previous slide? Yeah. Okay. Yeah. Thank you.
So the slides are going to be made available to you guys at some point. So, you know, if you, they will be on a website eventually and potentially in a Google Drive before then. So don't worry if you miss something quickly.
Yeah,
Okay,
you should be
thank
able to get these slides later. So once we've done the barocentric correction, it's time to extract the light curve. Now, you can do this in XSelect, as Kim showed earlier, but you can actually do it on the command line as well. So XSelect is actually a front end to many F tools behind the scenes. In fact, if you're in XSelect, you type, I think, echo or echo on, it'll show you the exact command line that it runs for each F tool that it's using. And so I did this for an example. And when I want to extract a light curve, it spits out that horrible line there. Many inputs, which a lot of just defaults, and we don't really care about. You can type extractor, and it'll prompt you for what you need to enter. But that is all the commands that extractor expects to extract a light curve. So there's the input event file, which has been barycentric corrected. To give it the energy band here, Kim said you did filter PHA could, but the XSelect translates that to this. You can select specifically after the file name this PI equals 30:1000, and that extracts the 0.3 to 10 kV band for you. If you don't do that, you'll get the full range, even the bits we don't outside the calibration. We give it the region file. I've used just a source circular region of 30 pixels radius here. You give it the output fixed light curve you're going to create. I'm going to choose a bin size of 10 times the native window time and time resolution. And I'll explain why later. But the native, in this case, it's about 0.018 seconds for 10 times resolution. And I'm also going to tell it that we want to select it for a specific good time interval, a GTI range. So there's a command line option called time file. You say time file and give it the name of this GTI file, which just has to contain the start and the stop times of the interval you're interested in. And they have to be in the correct time system that the event file is in. So in this case, it's the barycentric corrected times for this first snapshot of data. So if you get all that command right, it'll go ahead and extract a light curve at this short time resolution, 10 times the native resolution, over this first snapshot of data. And we can then use another F tool, or one of the Chronos, that's called Chronos, the time series analysis package in the F tools, in the eSolve software. And there's called PowerSpec, and this will generate a fast Fourier transform with the data set. And again, there are many command line options for this, and it will prompt you for the relevant inputs. But I've written them down here for this specific example. It can be quite confusing, I admit. There are a number of options here. So as well as the input light curve that we've just generated, there's this parameter called DTNB. So you can tell it to rebin the light curve if you want before it takes the power spectrum. But here, a DTNB value of -1 says leave it alone. I just want the native binning that's in the light curve. Then there's a number of time bins you want it to analyze. NVINT here. PowerSpec expects a power of 2, so I've said 4096 time bins. So it's going to take every 4096 time bins of data, generate a power spectrum, and combine them all together at the end in an average power spectrum. So in this case, from this snapshot of data, I think there were 11 intervals of 4096 time bins, which it averages. And once it's done this, we can tell it to plot the output, and you see this power spectrum on the lower left here. So on the lower left, it's without any. You can rebin. There's an option to rebin in frequency space. There's no rebinning in frequency space applied here. We see frequency on the x-axis and the power on the y-axis. And Without rebinning, you see a lot of bins at high frequencies. It's a log X scale. So there's a lot of bins at the high frequency end, and you can't really see much detail, but one option you can give it is this a rebin factor here of -1.02. I gave it. It will perform a geometric series rebinning in frequency space. So it will work out this geometric series based on this parameter. And you can see it is smoothed out. It is increased the frequency bins at the higher frequency end. So the noise is essentially suppressed as you rebin the frequency bins. So this showed the anatomy of a power spectrum when you have a QPO. So you have this noise level at high frequencies, which the normalization that power spec applies should be having a level of 2. That's just quasi noise. You see a low frequency rise. At low frequencies, the power spectrum is rising. And then sitting on top of that low frequency rise, you see this quasi-periodic signal. It's called a quasi-periodic signal because it's quite broad in frequency space. And in power spec, it will actually let you do a simple, it leaves you in this QDP window, and you can actually fit simple models to it. And in this case, I can find out the centroid frequency of that QPO. Now, so a bit more on the normalization then. By default, power spec normalizes the spectrum according to a paper written in the 1980s by someone called Leahy. So the quantum noise powers follow a chi-square distribution. And if you have averaged M power spectra and rebin them by, say, a factor of W, then the chi-square distribution will have 2 MW degrees of freedom, and it will be scaled by a factor of 1 over MW. So this leaves you with the noise powers distributed up to. If you had nothing but noise, you would have a flat power spectrum. It should be averaged around 2. But you can use this chi-square distribution to set detection levels, confidence levels, which you can be confident that you've got a detection of a given period, which is why it's very useful. Now, I've shown you this example here is a quasi-periodic oscillation, so it's quite a broad signal in frequency space. And the technique, people would say that to be most sensitive to QPOs, these broad signals, you should match your frequency binning to the QPO width if you can. So that's why you can give it this rebin factor to change the binning. You can either do that by dividing your data set. When you divide the native frequency resolution of a fast Fourier transform power spectrum is 1 over the duration of the data set. So if you divide that up into shorter durations, you end up with a larger frequency bins. So you can do that by averaging either over more intervals of data or by rebinning in frequency space. That lets you match the width to the QPO width. But if you're looking for coherent oscillations like you would get from pulsars, you want to maximize, you want to minimize the frequency bins. So you want the longest duration of continuous data that you can have, which then gives you the narrowest frequency bin. So there's different strategies when you're looking for periodicities. I've only shown you how to do this with the power spectral tool in Kronos. There's other methods available. Not all of them in Kronos, but one is the epoch folding called EF search. So if you have a period, you can define it. It will oversample in a frequency or period space, so you can actually get a more accurate period from an epoch folding search analysis. There's also other techniques which are available but outside of the F tools. One is that of a long startle periodogram. Again, you can also oversample in frequency space to get a more accurate period. It's also quite a useful technique if your data is broken up into gaps, because it helps minimize the window function somehow, which I can't remember how. There's also something called Zn squared, which applies to events directly in an event file. You should be aware of a number of things though. If you choose a time bin size which is just a small fraction larger than the native time bin size, so say you said it's like 5.1 times the native time bin size, you can create a beating artifact between the native time bin and the actual binning you've chosen. You can introduce fake signals into your light here. So that's why I chose a binning of 10 times the negative timing size, because you almost certainly don't see that effect there. So if you do have signals in a power spectrum, it's also always a good idea to try a different timing size in your analysis, just to see if it goes away. If it goes away, then it's something to do with the timing. So Kim mentioned pilot earlier, and for this particular snapshot for window timing data, it was not piled up. The count rate was below 100 counts per second, so it was fine. But when you have pilot, it can do two things. It can affect the noise power levels, and it can reduce the amplitude of detected signals. So there's a trade-off here. You can do the annular extraction to remove the core of pilot, which would then give you a pilot-free data set, but you may not be as sensitive. You won't have as many counts in the likelihood, which can make your search not as sensitive to detecting the signal. So there's always a trade-off to be done here. I mean, you can run this analysis on a corrected light curve. Kim mentioned XRTLC core earlier. You can correct your basically your extracted light curve for the effects of the core being removed, and but then it affects your noise powers in this power spectrum, because you're no longer simply dominated by Poisson statistics. But that noise power level may no longer be 2, and you have to make adjustments to that if you can. Then there's a problem with large data gaps. So I've showed you one small snapshot of data, well, it's 1,000 seconds long. And when you don't have gaps, this is all fine. You don't have really have problems with the data and windowing. But when you have gaps in the data sets, your power spectrum becomes a convolution of any true source signal with a windowed function of the data. So imagine you create a window function. You can say 1 when your data's on, 0 when your data's off, etc. And what the actual power spectrum you get out is then a convolution of the real signal with this window function. So it makes the analysis more difficult to see if what you're looking at is a true signal or something to do with window function. But along Scargill periodion, it can be actually less susceptible to this windowing behavior when you're searching for periodicities on evenly sampled data. So I've put a few resources here. So the paper Lee et al., which talks about the periodogram and the epoch folding analysis. That was one of the first papers out on the subject. There's a very good review by Van der Klis in 1989 on everything to do with Fourier analysis and X-ray timing for looking for signals, especially for QPO signals. There was a previous summer school in 2008, and Israel produced this set of slides, which has a very good introduction to time analysis in it. And there are plenty of papers in the literature, and one I've just cited here is by Barrett and Vaughan. It shows you how when you can fit functions in the power spectrum, and this shows you the correct methods to use for maximum likelihood fitting of these power spectral functions. And finally, there's a new analysis package for Python called Stingray, which I've not yet tried, but it does a lot of this and more. So it'll do the power spectral analysis, I think the long Scargill analysis, and things like this. So it will be well worthwhile investigating that in the future. I think that's it. So I think this is the end of the XRT section now. So if you have any questions,
yes, now is a good time for XRT questions. We've got half an hour or so of UBOT stuff for me to go through. So if you don't have questions now and you think of them later, that's fine. But if there is anything right now, you're welcome to ask. Likewise online, you can shout up if you have something, because I can't easily check otherwise.
I've got a question probably. It seems to me to bring that the resolution the special resolution of the 13 is 3.5 arc seconds.
The
spatial resolution.
The resolution is 2. The angular resolution is 2.3.
What?
What's the pixel size?
No, that's not what he's asking.
I thought you said spatial resolution.
Yeah, but what are you asking? Okay, I know what he's asking. No, it's the most accurate position we can get without enhancement, I think. It's 3 points. Yeah.
3.5. But the pixels area is 2.6.
2.36.
So my question is, when I size the core for the tie-up, should I size at least 2 pixels because the resolution is?
I would say yes.
Yes, I would say yes.
Yeah, I mean, I've never used less than 2 pixels. Honestly, there are very few times when I think that, you know, if it's piled up, I probably would usually want at least 3, but two would be fine. Yes, I would agree. 1 pixel is not a sensible.
So multiples of 2 pixels.
I don't think it necessarily has to be an even number.
Always something larger.
Yeah, and they're you know, not centered on things, but yeah, at least 2 pixels.
And for exercising values, would you just do it by eye again, looking at the data?
As in how much to extract? Yeah, I mean, it's all a bit approximate. There isn't a yes, that's exactly where pilot begins. So yeah, the plot that let's just whiz back up to the plot that I had. Oh, there we go. So if you plot it in linear space, as I did there, it makes it that little bit easier. And yeah, you basically just look for where that line starts being consistently above data. You will, I should say that, so we mentioned that pileup is usually above about 0.6 counts per second. If it's a very soft source, it can be noticeable down to about 0.3 counts per second. So both Andy and I work on Novi a lot of the time for our research. And you get a super soft source like the RS-off that I was showing. And it's because when the soft, if you have pileup, you basically get a pileup peak. So if most of the counts are at 0.7 counts a second, you get a peak at double that, approximately. Yeah. And it's very much more obvious if you have a super soft source because you've got all the soft things and then there's very little higher energy. So you notice by eye, so okay, that looks weird. But yeah, if you have a very, the whole 0.6 counts a second is approximately right for typical power law spectra, but it is not a hard and fast rule anyway. And if you are really concerned about pileup, always exclude more than it looks like it should be. The problem is, of course, then you get fewer counts, so your error bars get bigger on bits and things. So
the pileup will harden the spectrum. If you don't remove pileup, it will harden the spectrum.
Yeah.
It makes it totally index for power. So harden it.
go on, Shakala.
Yes, nice question. And in the first slide, you showed this source, which is extremely bright, right? And you mentioned that you went to the analysis of the WT data because probably with the kind of data. But if so, the situation is if one approaches a source, it doesn't know about the brightness it may have, and it goes to the online catalog. Does the online repository warns of the fact that the source might be so bright that PC data should not be used rather than
It will be used both, won't it?
So it depends who. If you are requesting an observation yourself and you don't know how bright it is, then go with auto state, because then XRT would automatically pick which mode. And the only time, even so, that I suspect we got, because if we don't know the position of a source initially, we can only measure positions in photon counting mode. So if there's a new transient from somebody like Maxi or anybody that does it, or even Swan and things these days who want a better position, the request has to be in photon counting mode because that's the only way that we can do it. And if the source is stonkingly bright, that's when we end up with things like that. But generally, if you don't know how bright something is, then you would go with auto state, and then afterwards, or you can look at the data and decide whether it ought to be typically PC mode. There are sometimes, I think we mentioned that the cut, changing between window timing mode and photon counting mode actually happens in different count rates depending on if the source is fading or brightening, because you don't want this one set thing. You'd end up with what we call mode switching. So if we'd said at count X, it's absolutely switched between WT and PC. If the count rate was pretty much at count X, it wouldn't really know which to be in. We had that occasionally at the beginning of the mission. But so if it's fading, something stays in window timing mode till 2 counts a second. I think it's 2 counts a second when you're fading to go down to PC mode, but it will stay in PC mode. If it suddenly re-brightens, it will stay in PC mode up to something like 10 counts a second, I think. I have to check the exact numbers. And it's, when we say these count rates, the count rate that is used to define which mode, if it's in auto mode, is actually not the count rate just of the source. It's the count rate at the center of the field of view. So this can complicate things if the background is high, because the average count rate will get bumped up if it's just looking at the central 200 pixels. So
you can have occasional problems when the source is outside the window timing window.
Yes,
so
so
in PC mode, it thinks it's very bright. It wants to go into window timing mode. Goes into window timing mode. There's no source in the window. It says, oh, there's no count there. I'm going back into PC mode.
Yeah, that's one thing we didn't mention actually. So PC mode is 600 pixels across. Window timing mode is only the central 200 pixels. So it's another way that we can read these things out faster. So yes, it can be that a source, while it's in the field of view of the whole CCD, is actually outside window timing mode. It doesn't happen that often, but
that particular source here, that PC image is over 100 counts per second. It should have been. That was taken just to get the position of the source, but it was taken way quite a bit after this initial data set. It was just brightening all the time, for over 100 counts a second. That's why there's a huge hole in it. But you can still get accurate position from that image.
Accurate enough. Right, last question, because we do have UVOT to get onto, and yeah, go for it.
So I looked into the XMM, and in XMM you have the soft proton background from in this case for Swift soft proton is excluded.
So yeah, we don't have to check the fact. Our background is typically very low.
Because we're in Earth orbit.
Yeah, so the XMM, it's because they're in a 48-hour orbit. That changes the background. So yes, you have to look for the flares in the background. No, you don't need to do that first. So yeah, that's. I used to work on XMM too, so I've done that many times. So in that respect, our stuff is easier. But yeah, low Earth orbit doesn't result in problems like that.
So episodes of high background and the sensors which are always due to other sources.
So we can get higher back. So I mentioned at the beginning the standard GTI filtering. There was this thing called the bright Earth. It had the elevation angle of bright Earth. If you look closer to the Earth limb, so as close to the Earth as you're allowed to, that can lead to enhanced background, particularly at the edge of the CCD actually, and that's what we call bright Earth. So that can happen. And it's also the temperature of the CCD. So we try to stick between -55, -65. If it gets above -50, you do tend to notice that the background gets yeah. So there are some things that can cause variable background for us, but it's not the soft photon things that XMM has to deal with. Okay, so we will move on to UVOT, because I certainly don't want to stop us all having the group photo and then lunch on time, but there's much less to go through with UVOT.